topic for this lesson is metal oxide semiconductor field effect transistors, MOSFETs. Metal oxide semiconductor FETs, or MOSFETs, do not have an actual p-n junction. When a metal oxide is not used to insulate the gate in the device, it is known as an IGFET, insulated gate field effect transistor. However, the gate is insulated from the channel source to drain current path in both types. Most commonly for a MOSFET, this insulation is achieved by using a thin slice of metal as the gate instead of the usual piece of semiconductor crystal. This slice of metal is oxidized on the side that is placed against the semiconductor channel. Metal oxide is a very poor conductor, so this layer of oxidation effectively insulates the gate. The semiconductor channel is backed by a substrate of the opposite type of semiconductor. That is, if the channel is made up of an N-type semiconductor, a P-type semiconductor is used as the substrate. IGFETs with P-type semiconductors are less common. The basic structure of an N-type MOSFET is shown in this figure. The second figure shows the symbol for MOSFETs. There is a fourth lead connected to the substrate for this type of MOSFET. The IGFET symbol is shown in the third figure. The direction of the arrow here is reversed. For proper biasing of a MOSFET, the substrate is usually kept at the same voltage potential as the source. This is shown in the diagram. The above discussion entailed MOSFETs, also called depletion MOSFETs or D-MOSFET. A D-MOSFET, however, can operate in the depletion mode. Depletion mode devices, JFETs, IGFETs, reduce the current flow by increasing the negative voltage applied to the gate, assuming an N-type channel. In the enhancement mode MOSFET, or E-MOSFET, the source and the drain are not parts of a continuous channel of semiconductor material. The basic structure of a typical enhancement mode FET is illustrated in the figure. Enhancement mode FETs always have an insulated gate. The symbol for an N-channel enhancement mode FET is shown in the second figure. For a P-channel enhancement mode FET, the direction of the arrow in the substrate line is reversed, as shown in the third figure. Considering operation, assuming an N-channel device, a positive voltage is applied between the gate and the source. The higher this voltage is, the greater the number of holes drawn from the N-type source into the P-type substrate. These holes then traverse into the N-type region, drawn by the voltage applied between the drain and the source. Thus, increasing the voltage on the gate increases, rather than decreases, the channel current, the current from the source to the drain. The D-MOSFET can operate with either positive or negative gate voltages. The point on the characteristic curve where V sub GS equals 0 corresponds to I sub DSS. The point where I sub D equals 0 corresponds to V sub GS off. As with the JFET, the off voltage G sub S is equal to minus V sub P. Let's look at an example. For a certain MOSFET, I sub DSS is equal to 20 milliamps, and the off voltage V sub GS is equal to minus 9 volts. Is this an N channel or a P channel? The device has a negative off voltage V sub GS, hence it is an N channel. Calculate I sub D at V sub GS equal to minus 4 volts. Using the equation shown, I sub D is equal to 6.7 milliamps. Calculate I sub D at V sub GS equal to plus 4 volts. Using the equation shown, I sub D is equal to 41.7 milliamps. The E-MOSFET uses channel enhancement. From examining its characteristics, we find that I sub D equals 0 when V sub GS equals 0. Thus, the E-MOSFET does not have a significant I sub DSS parameter as does the JFET and the D-MOSFET. Ideally, there is no drain current until V sub GS reaches a certain non-zero value called the threshold voltage, V sub GS threshold. The drain current is then expressed as shown. The constant K depends on the particular MOSFET and can be determined from the datasheet by taking the specified value of I sub D, called I sub D on, at the given value of V sub GS and substituting into the above equation. For example, the datasheet for a certain E-MOSFET, a 2N7008, gives I sub D on equal to 500 milliamps for V sub GS equals 10 volt and V sub GS threshold of 1 volt. Determine the drain current for V sub GS equals 6 volts. Solving for K, we get K is equal to I sub D on divided by V sub GS minus V sub GS threshold, or 6.17 milliamps per volt squared. Using the value of K for V sub GS equals 6 volts, I sub D is equal to K times the quantity V sub GS minus V sub GS threshold squared, or 154.25 milliamps.